If we want to make two vectors that are orthogonal to 1, 0, 1 and orthogonal to each other, let's say we just call those u and v. And we want them to be orthogonal to 1, 0, 1 and orthogonal to each other. How do we check if two matrices are orthogonal? Or what has to be true to make that happen?
Dot product is equal to 0.
Yeah. And so we really have three dot products we need to check. So we've got two vectors. We want them both to be perpendicular to 1, 0, 1. So u dot 1, 0, 1, let me write these on separate lines. U dot 1, 0, 1 must equal 0. And v has to be orthogonal to that same vector. So v dot 1, 0, 1 has to equal 0. And also we want them to be orthogonal to each other. So u dot v must also equal 0. And since the only thing we know about u and v is there's some sort of 3x1 vector and these three equations must be true, what I would usually do here is just assign variables. We know u is some 3x1 vector. So let's just make up some variables. Let's say a, b, c. And v is also some 3x1 vector. So let's just call that x, y, z. And this is often a very useful approach. If you want to create a matrix or a vector or a polynomial or a function or whatever that has certain properties, make up the or write out the structure you want it to have, assigning variables to any unknown values in it, any parameters or entries or whatever. And then write out any properties you want it to have as equations. For example, if we write out vector u dot 1, 0, 1, what would that look like in terms of the variables?
A plus c.
Yeah, a times 1 plus b times 0 plus c times 1 is just a plus c. So in order for this to be true, we know a plus c must equal 0. And likewise, if we write out v dot 1, 0, 1, what would you get?
X plus z.
Yeah, x plus z also has to equal 0. Those alone will guarantee that u and v are both orthogonal to 1, 0, 1. As long as a and c add up to 0 and x and z add up to 0, regardless of what b and y happen to equal. But we also have the restriction that u and v have to be orthogonal to each other. What would that look like as an equation?
A x plus by plus cz.
Yeah. A times x plus b times y plus c times z, that's the dot product of those two vectors. And we're assuming that that has to equal 0 so that they're orthogonal to each other as well. So that gives us three equations that have to be true. But how many unknown variables do we have?
Six.
Yeah, we've got 6 unknown variables, but we have only 3 equations. That suggests there should be, or there at least could be, infinitely many solutions to this system of equations. Generally, if you have more unknowns than you have equations, that usually means there's not enough information, not enough equations to narrow it down to a unique solution. So we should expect there's infinitely many vectors that make this work. But we can use these 3 equations to at least figure out how these 6 values have to be related to each other. For example, if a plus c equals 0, what does that tell us about a and c? For example, could you solve for one of those variables?
A equals c. A equals negative c.
Yeah. Which means in the original setup, everywhere we see a, we can replace it with negative c. And likewise, if x plus z has to equal 0, what does that tell us?
x equals negative z.
Right, which means everywhere we see x, we can replace it with negative z. So each one of these vectors originally had 3 unknown variables, but we've used these facts, these equations, to narrow it down to only 2 unknown variables each. We can also even make that substitution in the third equation here. Every a can be replaced with negative c. Every x can be replaced with negative z. And negative c times negative z is just cz. So we get c times z plus b times y plus c times z equals 0. We could also combine these cz and other cz. So 2 times c times z plus b times y has to equal 0. So now we've narrowed it down to only 4 unknowns, c, b, z, and y. And we have one fact about how c, z, b, and y have to be related. Any questions on that so far? So we can now think of this as one equation, since we've already got all the information we need from these. We can now think of this as one equation with 4 unknowns. So there's, of course, still going to be infinitely many solutions. But with this one equation, you can solve for one of those variables. You can isolate one of these variables in terms of all the others. So for instance, which one of these variables do you want to solve for? Well, keep in mind b and y are separate variables, so we want to solve for one or the other of those. Let's say we want to solve for variable b. If you isolate b here, what would you get?
Minus 2cz divided by y.
Yeah. So this is the one extra restriction that we know has to be true. The previous restrictions that a has to be negative c and that x has to be negative z, those guaranteed that each of these vectors was orthogonal to 1, 0, 1. This extra restriction that b has to equal negative 2 times c times z divided by y, that will guarantee also that the vectors are orthogonal to each other. So we can now write out both of these vectors in terms of only 3 unknown variables instead of 6 unknown variables. Any questions on that work so far? So let's try writing out the final vectors. We know a has to be negative c. B, it turns out, has to be negative 2cz over y. And c could be anything. And then for vector v, I guess we could just leave it as this, negative z, y, z. Because the only restriction on x was that it has to equal negative z, and we got no restrictions on y and z. So we could say we're treating z, y, and c as free variables. Free variables in the sense that those 3 values are free to be any real numbers. But the other values, a, b, and x, have to be replaced by these formulas in order for this to work. Any questions on that so far? So we now have formulas, not just 2 vectors, but we have formulas for creating any 2 vectors that will make this work. We can create vectors by just choosing values for c, y, and z, filling them in to get a specific pair of numerical vectors. So if we just need a vector that works, or a pair of vectors, I should say, we could just choose any values we want for c, z, and y and fill those in. And of course, we don't want them to all be 0 because we want a vector that's not just the 0 vector that makes this work. So for example, let's try picking some numbers. Give me some values for C, Y, and Z. Just pick some numbers to use. It can be anything you want as long as they're not all 0. And of course, Y can't be 0 because then we get a division by 0 problem. Let's try 1, 2, 1, sure. In that case, U is going to be negative C, so -1. -2 times C times Z, so -2 times 1 times 1 is -2, divided by Y, so that'll just be -1. And then C is 1. And then for vector V, using the same values for C, Y, and Z, -Z, so that's -1. Y, so that's 2. Z, so that's 1. So we're claiming, according to the formulas we just created, these vectors should fit the description. How can we check that it really does work? How could we verify that these really match the description that we started with? Yeah, take the dot products. We wanted U.101 equals 0. If we try that dot product, -1 times 1 plus -1 times 0 plus 1 times 1, that's -1 plus 1, so that's 0. So we verified that this is a vector that's orthogonal to 1, 0, 1. If we try the same with V, V.101, -1 times 1 plus 2 times 0 plus 1 times 1, -1 plus 1 again, so that's also 0. So V is orthogonal to this vector originally. And lastly, we want to check U and V together, U.V. So U.V, we got -1 times -1, -1 times 2, and 1 times 1. 1 plus -2 plus 1 is 0. So that verifies that U and V are also orthogonal to each other. So we've just created two vectors that fit this description. They're both individually orthogonal to 1, 0, 1, and they're orthogonal to each other as well. Geometrically, we've just taken, let's say 1, 0, 1 is in this direction. We've created two vectors that are perpendicular to 1, 0, 1 and perpendicular to each other. So we've created essentially a coordinate system. We've created three axes that are perpendicular to each other. We could use that as a foundation of a new coordinate system if we needed to. Any other questions on that? And of course, we didn't have to choose these two vectors specifically. You could have chosen any value for C, any value for Y, any value for Z, as long as they're not all 0. And you should get two vectors that make this work. Any other questions on orthogonality or anything else you want to work on?
This was really helpful. Thank you.
Yeah. And I think this in general is a very useful method. If you want to create a vector or a matrix or a polynomial or anything that has certain properties, just like we did here, create or write out the format you want it to have in terms of variables, A, B, C, or whatever, using as many variables as you have things in that equation, in that structure that you don't know. And then write any properties you want it to have as equations. Ideally, that should give you a system of equations that can be solved. Hopefully, they'll be linear equations, so you can use matrix methods to solve it if necessary. But even if some of them are nonlinear, like we got the AB plus C, or AX plus BY plus CZ, that's a nonlinear equation because we've got unknown variables being multiplied by each other. But we can still use substitution techniques to get more information from it. And then solve for some variable in terms of the other variables, and then you at least have a formula for what the result should look like. Any other questions on that?
I just have a quick concept question. It's a little different from this again.
Mhm.
So the span basically all linear combinations?
Yeah, the span of a set of vectors means the infinite set of all possible linear combinations. I tend to think of the vectors as kind of like building blocks in this context.
Mhm.
Like if you've got a few vectors, the span of those few vectors is everything you can build using just those vectors. Like let's say we have two vectors, A and B. These are two vectors. If I put them in curly brackets, this is now a set of two vectors, a set containing those two vectors, and that's it. But if I say span of these two vectors means not just those two vectors, but also everything you can build by linear combinations. So that's going to include A itself and B itself, because you can get 1A plus 0B, that's A, or 0A plus 1B, that's B. It'll also include the zero vector, because you could say 0A plus 0B is the zero vector. It's also going to include 2A minus 3B and square root of 5A plus 19B and A minus pi over 2B. How many vectors are going to be in this set? If we wanted to list out all linear combinations, how many possible linear combinations are there?
There's infinite.
Yeah, this is going to be an infinite set of all possible linear combinations. And of course, writing it out as a list is kind of nonsensical because there's infinitely many of them. So instead, a very useful notation for writing out a set of infinitely many things, but that follows a certain pattern, we would often write this in what's called SetBuilderNotation. And the way that's usually written is you write out the general format of things that are in this set. And linear combinations of A and B are just going to be some scalar times A plus some scalar times B. Let's call those, let's say, C1 and C2. But note that we haven't defined C1 and C2 yet. A and B are already implied by the notation. A and B are just some vectors we know, presumably. But we need to describe what we mean by C1 and C2. So we typically write this as set notation, curly brackets, the set of the general format, and then this bar is usually read as such that. So you've got the general conditions, or general format, I should say. General format of things in this set. And then on the right side of the such that bar, we write any restrictions on the things in the set. Like for instance, we've just introduced C1 and C2. What do we want to imply about C1 and C2? What sorts of things could C1 and C2 be? Like if we just introduce new variables, we have to explain what they represent. What do we mean by C1 and C2?
Constants.
Constants. Specifically, what kind of constants? What kind of values are they?
Real numbers.
Yeah, they could be any real number. So on the right side, we're just going to write C1, C2 belong to the set of real numbers. So this is kind of declaring what we mean by our notation here. And also if there's any restrictions, like if we wanted to specify that C1 and C2 had to be positive numbers, we'd include that on this side of the equation. But this, or not a side of the equation, but this side of the such that bar. So the right side here, this section is representing any restrictions necessary to make it be part of the set. So this is usually called set builder notation. It's useful not just for span. I mean, we can use it to define what we mean by span, but it's very useful in general for describing any infinite set of things. Instead of trying to write out all infinitely many things, we just write it out in this set builder notation. A general format for the sorts of things that are in this set, a bar that we read as such that, and then a list of any restrictions that are necessary to really count as part of this set. And this might be for an infinite set. It might be describing a finite set. Maybe there are only finitely many things that make this restriction true. It might even be the case that the set is empty. Maybe there's nothing that makes that restriction true, so there's not really anything in the set at all. Any questions on that notation so far? So for example, one way we could write a set builder notation, just as one other example, let's say let S equal the set of all vectors X, Y, Z in R3. So on the left side, we're describing the general format of what sort of thing we're talking about, such that, and then on the right side, we can write out any restrictions. Like let's say our restrictions are X plus Y plus Z must equal 0. So this is the sort of thing in the set such that, and then a list of any restrictions that have to be met in order for the thing to really count as part of the set. So this would be a set of, and would this be infinitely many vectors? Are there infinitely many vectors that could make this restriction true? Let's see if we can figure some examples. Like what would be an example of a vector that makes this restriction true, something that really is a member of this set?
One, 0, -1.
Yeah. The vector 1, 0, -1. That definitely makes it true that the X value plus the Y value plus the Z value equals 0. So that means this is a member of set S. Any other examples?
Two, -1, -1.
Yeah, that should work. The X, Y, and Z coordinates add up to 0. So this is also a member of set S. And it looks like we could build more as well. We could construct probably infinitely many, because you can basically set maybe 2 of the variables to anything you want. And then the third one is just whatever you have to add to cancel them out. So set S is an infinite set. There's infinitely many vectors that make this restriction true. Any questions on that notation so far? And another way we can describe this set in particular, not every set of vectors, but this set we should be able to describe as the span of a few vectors. So let's see if we can figure out what simpler vectors we can use to span this entire set. Of course, these are going to be some examples of those, but let's see if we can describe it more generally. And we can use the same sort of approach. We can say, let's say we've got some vector little s that's equal to, let's call this A, B, C. And in order for this to be a member of set big S, what has to be true about the values of A, B, and C? Can you write membership in set S as an equation?
With the restrictions?
Yeah, we're talking about this same restriction. So we want to write out this format of equation, but using these variables. So what would that look like?
Oh, A plus B plus C equals 0.
Right. So again, we've written out the general format of the sort of thing we want. And we've written the restriction. We've written the property we want it to have as an equation. And in this case, we just got one equation. So it is technically a system of equation. Well, system of equation. We have one equation, 3 unknowns. which means we can't pin it down to just one example. We should expect infinitely many solutions here anyway. But since there's only one fact about three variables, that means we can solve for one of those variables in terms of the others. So for example, if you solve for one of these variables, what would you get?
A equals minus B minus C.
Yeah. So we have the one restriction, the one requirement for this vector can be written as A equals something about B and C, which means we can treat B and C as free variables. According to this equation, B and C could be anything as long as A equals negative B plus negative C. So we can make that substitution in our original framework, the original ABC vector. So vector S can be written as this exact format, but we're going to replace A with negative B minus C. So we've narrowed it down from a vector with 3 unknowns to a vector with only 2 unknowns. And we can't really narrow it down any further because this was the only requirement for the values of A, B, and C. But what we can do, since we've got it down to 2 unknowns, we can split this up into a vector that's just about B and a vector that's just about C. If we split up the top value, negative B plus negative C, we can split that into negative B in one vector plus negative C in the other vector. Likewise, B, we've got just one B and no C at all. So I'm going to put a 0 here. And then for the third coordinate, we've got one C, but no B at all. So I'm going to put a 0 here. So we've rewritten our original vector, which had 3 unknowns, as a new vector, well, really the same vector, but with only 2 unknowns, and split that up into 2 vectors, each of which has only 1 unknown. The reason we want to do that is that now that each vector has only 1 unknown, since every term in this vector has B in it, or just 0, what can we do with B there? If it shows up in every term. Yeah, we can factor that out. If we factor out B, what's left in this vector?
Negative 1 and 0.
Yeah. And compare that to the original definition, x plus y plus z. If we add up the coordinates of this, what do we get?
0.
Yeah, so that means this vector, negative 1, 1, 0, is a member of set S. And if we factor out C from this vector, what do we get?
Negative 1, 0, 1.
Right, which also fits this restriction. X plus y plus z, negative 1 plus 0 plus 1 is 0. So we ended up finding a couple of specific numerical vectors that make this true. But also what we've just found is that if S is any vector that makes it true, then that vector can be written as a linear combination of this vector and this vector. So we've just found what we call a basis for set S. That is, every vector in set S can be written as some linear combination of this vector and this vector. In other words, S is the span of these 2 vectors. We can say S, the set, equals the span of these 2 vectors. Negative 1, 1, 0, and negative 1, 0, 1. And this is often much more convenient than having a description like this, because instead of describing set S based on some property that its vectors have, we're now describing set S in terms of what building blocks you need to construct everything in that set. So you can now use this as a recipe for building any vectors in set S you want. If you just want to find like 10 vectors that has this property, just choose 10 pairs of values for B and C, and this formula will give you 10 new vectors that are all members of set S, that all have this property. And the usual terminology we would use here is we would say these two vectors, -1, 1, 0, and -1, 0, 1, are a basis for set S. And that's not just one vector or the other, but the two vectors together form a basis for set S. And by basis, we mean a set of vectors that's enough to span the set. That is, the span of these vectors is the whole set we're talking about. And also there's no redundancy. There's no overlap. There's no way we could have spanned this set with fewer than these. This is the bare minimum for spanning set S. And it certainly could have been written other ways as well. We could have written this one as like 5, -5, 0, and 10, 0, -10. Those would also work as a basis for set S. So there's infinitely many ways you could write a basis. But all those ways of writing a basis are going to include exactly two vectors. You need two vectors to create this set. You can't do it with just one. And what does that tell you geometrically? If you're looking at the span of two vectors, all possible linear combinations of two different vectors, what shape are you building? Like if this vector is in some direction, you can go as far as you want in this direction, and this is in some other direction. You can go as far as you want in this direction. If you can go as far as you want in either of those directions, what shape are you constructing? Yeah, you're creating the entire plane. So these two vectors span an entire plane of points that make this true. And how many dimensions would you say a plane has? Three-dimensional would be if it was like if you took the plane and extended it into a third dimension. But a plane, a flat plane, is just two-dimensional. It's in a three-dimensional universe, but the plane itself is two-dimensional. And the reason we call it two-dimensional mathematically is because you only need two vectors to build it. The span of two basis vectors is going to be a two-dimensional space. The span of three basis vectors would be a three-dimensional space, and so on. When we talk about dimension of a space, dimension of a set of vectors, we mean how many vectors do you need to span that? How many vectors are necessary to build that set? So we'd say set S is two-dimensional because you need two vectors to build it. You need a basis of two vectors. And that'll be true for any basis of this particular set. You might get different vectors, but you'll get two of them. Any other questions on that so far? Also, looking back at the idea that we got two vectors because we needed one that we factored B out of and one that we factored C out of. Why do we have specifically two free variables B and C here? Why didn't we have one free variable or three free variables? If we go back to when we solved for, we started with A plus B equals C, or sorry, A plus B plus C equals 0. And we were solving for what?
A.
Yeah, we solved for A. And we didn't have to solve for A in terms of B and C. We could have solved for B in terms of A and C, or solved for C in terms of A and B. But either way, we've got one equation, but three unknowns. So that means we're solving for one variable in terms of the other two. The fact that we had two more unknowns than we had equations meant that we ended up with two free variables. B and C could be anything. And two free variables translates to two basis vectors. So we end up with a two-dimensional space because we had two free variables in the restriction. Three-dimensional universe, because we've got R3 here, but one restriction narrows it down to a two-dimensional space. Any other questions on that? And if you want to get some more practice on this, it's pretty easy to make up more examples. If you just write out in SetBuilderNotation, let S or whatever variable you want to use equal the set of vectors in R3 or R4 or R2, whatever you want, such that, and then just make up some restriction, whatever restriction you want, and see if you can find a basis for that. It's not always going to be possible. Some sorts of restrictions might lead to a result where you can't form all of them by linear combinations of a few basis vectors. But try experimenting with different restrictions and see which ones do lead to a few basis vectors that span the whole thing and which ones don't. Look for patterns in those and explore different ways of getting it. So give that a try. Let me know if you have any other questions, and I will see you next time.